Okay, so I have started recording. So let me start the class. Okay. So where were we? We just completed the discussion on forward pass in a nutshell, or sort of forward pass in a multi-layer neural network, right? So it can have many layers. Actually, this way. So it can have many layers. The first one is called the input layer. So, I mean, you can also take it as the 0th hidden layer. The intermediate layers are called hidden layers, and the output layer is called the output layer. I mean, the layer that gives you the output is called the output layer. And these are the notations that we have seen, that X is input, which is equivalent to H0. Then it goes through a linear operation, that is W times X plus B, which gives you the pre-activation, which is denoted as A. Then it goes through an activation function, which gives you the activation functions. Oh, sorry, activation values. Then these activation values becomes the input to the next hidden layer. So it goes again with linear operation. It gives you pre-activation, goes through activation function, gives the activation values, and so on. And ultimately, finally, for the final layer, the pre-activation goes through the output activation, which, I mean, why are we differentiating between the output activation and these hidden activations? Because generally the output activation is different, its purpose is different. So generally this is different from the others, but it can be same with the hidden layer activations also for some, say, regression values, regression problems, where you know that the output is between 0 and 1. A scalar between 0 and 1, something like that. So, but yeah, I mean, in general, it is different. So that's why it is denoted as O. Now, these are the operations, that is this, and this. So we said that we want to basically, our objective is to find the, sorry, 2 times, okay. Our objective is to find the theta that actually reduces the cost. Cost basically means some sort of a measure of how, measure of deviation, you can say, from the true value of the output and the output that you are getting, that predicted value, that is fx theta, and C is the true value, right? For a classification problem, C is the true class and fx theta is the predicted class. So for that, we have already discussed about gradient descent. So we need to, I mean, if you are minimizing a cost, then you have to find the gradient. So for that, we need to, and what are the learnable parameters? These W's and B's, right? So the weights and biases. So these gradients you need to compute, because after that, what you will do is your new W is this old W minus step size times del J del W, right? For all Ij, I am not writing Ij and L here. So L, you know, the superscript L is, I mean, denotes the layer number, right? So W and B are basically specific to all the layers. So this is the first layer, or this is the Lth layer, this is the L plus 1th layer, this is the capital L, which is the last layer, and so on. So for gradient descent, we need to compute this for all I, J, and L. So now the way we compute it is called the backpropagation, and it is nothing but just an intelligent use of chain rule. So if you just see the backpropagation in a whole, as in a slide or in a page, it might look cumbersome, but actually it is pretty easy. I mean, it just uses chain rule. So let us try to dissect the backpropagation rule a little bit. So let's go ahead. Oh, sorry. What happened? Yeah. Okay. So yeah. So W. So we are after this Wij W. Sorry, del J del Wij. So let us see how can we find it. So one fact is that this Wij, or I mean, this is a matrix which is all the collections of Wij for this L's, right? For this L particular layer, and BL is a vector which is a collection of all BI's for this L. So just think about one of them, just one Wij L. So what does that mean? So basically you have these sort of, I mean, these are also coming from somewhere else and so on, right? But this is one layer L, for which you have the input basically H, right? HL minus 1. This is HL minus 1. And you have another these A nodes, right? Something like this and go on, so on. So this is connecting here, this is connecting here, this is connecting here, and so on. So one of them is this Wij. This is Wij. And what was our basically notation? That the one, this the first subscript is this I, and this is the J. So basically jth neuron in L-1th layer that connects to the ith neuron in the Lth layer. So this is the Lth layer, and this is the L. Sorry, this is L-1, and this is L, right? So in L-1, this second superscript, that is in Wij. Remember it. I mean, to the way to remember is J to I. So J to I. So this is J, and this is I, right? So now for any particular one particular specific Wij, what happens? It happens is that Wij influences AI. So Wij does not influence anything else. It does not go to there. It does not go to there. That is a separate Wi. It may be Wi plus 1j. It may be, this may be Wi plus 2j, and so on, right? So this one Wij influences one AI, right? And that AI in turn, with a series of other operations, basically gives you the J. So this is one way of looking at what I am telling here. Another way is that, okay, J is a function of AIL. So J is a function of this AIL, which is this, right? I mean, I think I was taking this, and this AIL is in turn a function of Wij, of this, that is some Wij here. Both are equally true. So if I say Wij influences J through AI, that means Wij influences AIL, then AIL actually gives you J. Similarly, J is a function of AIL, and AIL in turn is a function of Wij. And there is nothing else to basically understand here. If you just focus on this statement, then your calculus, I mean, not even first year, I think +2 calculus says that del J del WIL is del J del AIL, and del AIL del WIJL, right? So this is the chain rule. So so we need to get this del J del and del AI del IJ, sorry, del AIL del WIJL. So this second term, let us see how we can get, and you can understand how we will go about it, because what is the relation between AIL and WIJL? Let us try to write it. So this is AI. So let me just try to give one different color. Maybe this. So this is AIL, and this is, as I said, WIJL. So what is the relation? This is the relation. So AIL is basically WI1, that is 1 to I, H1L minus 1, H2L minus 1. This is multiplied with WI2, that is 2 to I. So this is H1, this is H2, and so on. So this is how you get AIL, but only you are interested with WIJL, which is here. So if you take the partial derivative this, what will be it? Only this, right? And that's what we are doing. Del J del WIJL is, or sorry, del I mean this part, del AIL del WIJL is this on, because from here you will only get it, right? Only this term will stay. Others are constant with respect to WIJL. So only this. Similarly, if I mean we want to get del J del BIL, right? So not this, just this also, and see very similar rules. So del J del AIL and del AIL del BIL, right? And what is the relation between AI and BI is this. So if you take the partial derivative, it is just 1. I mean, this part is 1. So this is only del J del AI. So you see that, I mean, let me discard all this here, clear pen markings. So this is what you are getting. So this is this, and this is this. Now, what does this, I mean, if I want to see, we are after these two, right? So to compute this, we need this, and this. See that del J, del AIL appears in both the equations, 1 and 2. So we will go to see how we get the del J, del AIL. But at least this we have got from the forward pass, right? HJL minus 1. HJL minus 1 from the forward pass. So for a particular X, you have already done the forward pass, computed the J, and then you are doing the backward pass. Now, why it is called backward pass, I will come. But at least from the forward pass, you have got this HJ. So you are after this del J, del AIL. Let us see how we can get del J, del AIL. Now, just try to recapitulate what you have done. So we are first, I mean, in this slide, we were after del J, del Wij. So what did we try to see? That, okay, what is the immediate thing that is Wij is influencing, and then whether that is influencing J or not. So Wij is influencing AI, and then that is influencing the cost J. So we can say that J is a function of AIL, and AIL in turn is a function of Wij. Same idea will go ahead with del J. I mean, when we want to find del J, del AIL. So what is AIL influencing immediately? Then if that is influencing J. So yeah, so we know this from the forward pass. So we need del J, del AIL. So very, similar motivation. AIL influences J through HIL. Because what was the relation between AIL and HIL? I'm not writing it. So it is between pre-activation and activation. And it goes through an activation function then. So pre-activation going through an activation function, it gives you the activation values. So the what is that called? Sigmoid, or the tan H, or the ReLU. So this was the A values, and this axis were giving H, right? And it was element wise. So if A is a vector, this is like separately, this is a G, because G was the notation that we used for activation. This is the same G, this is the same G, but element wise, that is separately these are operating. So if this is A, this is H. So basically, if this is A1, this is H1, if this is A2, this is H2, and so on, right? So J is a function of HIL, and HIL is in turn a function of AIL. So same rule, chain rule. So del J, del AIL is del J, del HIL, del HIL, del AIL, right? So what is del HIL? I mean, the second term, that is this. The relation is this, right? H is related to A via G. So del H, del AI is G prime, and G primes, you remember, you got it in a previous slide. Sorry. Now how can I go there? It's a bit early, right? Okay, let me close the slide. So it's not. Discard. Yeah, this one. So these are this is G. Oh, sorry. Yeah, this is G. And this is G prime, right? So this is G, this is G prime, and so on. So this G prime you can get from here, right? Let me go to the actual slide now. This one, I think. Yeah, now here. Yeah, so we are getting G prime as this term. So what is next? So we know G prime AIL from the forward pass. Because why? Because G prime is a function of G. I mean, for sigmoid, it is G into 1 minus G, if I remember it correct, right? So you have the values of G prime from the forward pass. So you get this from the forward pass. So you are left with this del J, del HIL, right? So before I go to get del J, del HIL, I see there is a raised hand. I'll go there. Yeah, but I mean, next time, I mean, again, the motivation will be same. Like you are trying to find del J, del HIL. So what is, I mean, HIL, what it is influencing, and is that influencing the cost function? So again, before I go to address that question, just a recapitulation from the last slide. We are after del J, del W, let's say not tell so much of IJL, del J del W and del J del B. For that we have seen at the end of this slide that we need del J del AI. Now del J del AI, we have seen that for that we need again del J del HIL, right? So we'll see how can we get that. So let me go through. Gautam Sagar. Yeah, Gautam, I have asked you to unmute.
Sir, in the equation 3, we are using the derivative of G, but
Yes.
that means the activation function needs to be differentiable, but the ReLU activation function is not differentiable. So how will we use it here?
Yeah, it's a good question. It's a very good question. I have touched this question a little bit when I discussed about the derivative of ReLU. So let me actually go there. It is actually differentiable in a sense. It is you have to apply a particular type of a method that's called the subgradient. So subgradients is sort of a midway between getting gradients for a continuously differentiable function and slightly I mean, which is not different. I mean, I would say it's not discontinuous, but there are some points where you can have many different gradients. So for example, though this is a concept that is better told in optimization. Where was that slide? Yeah. I mean, just to give you an idea, what happens is that here, for example, this G, for a greater than equal to 0, that is this part, it is 1, right? And for here, the gradient is 0. But what happens here? You can think that it can be any, I mean, if you just think gradient as the tangent. So in subgradient, the idea is that you can take any tangent between this one and this one. So the tangent for this part is this, and the tangent for this part is this. So you can take any gradient randomly taken from here to kind of replace or to kind of give a proxy to the gradient at this value. And the idea is that why does it occur? Because there is only one place where this is happening, and maybe it will not encounter much. If there is any noise or if there is any error that is creeping in, that will not creep in much many times. So this is again a very high level idea of how you can deal with it. If you are interested, you can just go and look for any optimization literature where subgradients are there. There are other ways, but at least I know this way. Okay. Hopefully that answers your question. Any other questions? Okay, let me actually go. If you have any questions, you can ask at that time. Okay, I was probably here. Just 1 second. Let it come. I was in the previous slide. Yeah. So we need to know this del J del HI. And as I said, the motivation or how to go about it is what is H that is influencing, and which in turn is it influencing J, right? So what is H influencing? So yeah, this is a little complicated part. Just stay, I mean, focused here. The thing is that, but I mean, it's complicated, but all the things, all the tools you know. So you just need to basically bring them together. So HIL influences J through A1 to ML plus 1 L plus, I mean, the layer of layer L plus 1. What does it mean? This means that these were the H's for, say, Lth layer. So these are some, let me try to draw it in a very clean way. So this is the Lth layer. And then you have, suppose, this L plus 1th layer where you have the A's, right? So this is H, this is A. Now, we are trying to find what HIL is influencing. So suppose this is the HIL, right? This one, basically. I mean, I'm not drawing the second one from the top, okay? So this is actually, okay, let me draw another one here. So it is actually giving a weight there, and a weight there, right? So what I'm saying by when what I'm meaning when I'm saying that HIL influences J through this is A1, this is A2, this is A3 of the layer L plus 1. I can write it just for the sake of completeness, right? So HI is influencing A1, A2, A3 all. That is given by this notation, A1 to ML plus 1. What is ML plus 1? It is the number of nodes that is there in L plus 1 nth layer, right? So I hope this is clear what I mean by HIL influences J through A1 to ML plus 1. That means HI is in giving its contribution to all the neurons in the next layer, right? That then all of them actually with a series of other computations, it is computing you, giving you the J. At least this part is clear. What I mean by this, I just wait for say 5-10 seconds. Hopefully. Okay. Now, that means again, I mean, the same statement taken from say bottom down. Okay. So, sorry, top down. Yeah. So then that means J is a function of A1. Again, I mean, it is hard to tell, but yeah, A1 to ML plus 1 of L plus 1th layer. And each of these is in turn a function of HIL. So J is a function of all of these because HI is influencing all of these, and that in turn is influencing J. So J is a function of all of these, and each of them is a function of HI. So now we will go into a little kind of extension of the chain rule. If I mean, this is, remember, I mean, this probably you did not encounter it in your plus 1, but at least I'm sure in multivariate calculus, whatever the name was, probably mathematics 1 or 2 in your first year, that you have encountered. That if U is a function of say two variables X and Y, and X and Y are functions of a single variable T, that is X is a function psi phi T and Y is a function of psi, Y is a function psi T, but both are a function of P. In that case, del U del T, what happens is just you have to sum the chains, right? So del U del X, I mean, if it was just a function of X, that is if you were just a function of X and X is a function of T, just this term would have come, right? Del U del X and then del X del T. But it is in addition a function of Y also. So you add them. So del U del Y del T. So this is the rule that you will employ. In your case, U is J, right? Here I can write X is A1, Y is A2 to ML plus 1, right? And all of them is a function of T, where T is HIL. So I'm just giving you again 10 seconds to look at it. What is U? What is X, Y? What is T? This is U. These are X, Y's. This is T, right? So you then employ this, right? So you just basically, now it is very simple. So del J del A and del A del HI, right? And you sum it over all A's, that is M1 to ML plus 1. So now what happens? I think let me discard it. The pen. Yeah. So now what is the relation between A and H? This is A and this is basically the how it is related to H. So in the next layer, it is 1 to M multiplied with H1 from previous layer, 2 to M multiplied with the H, I mean the second H from the previous layer, and so on, right? And this is I to M. So if you are trying to find the derivative of this thing with this, that is this, only this part will remain, right? That is what we are doing. So here you have this del J del AM L plus 1, right? So you are getting finally del J del HIL. So this is the fourth equation. Again, just a small recap. In the very first, okay, I think it is better to. So in the last slide, we are, let it come here. We are getting del J del HI, right? And here Okay, del J del HI. Del J del HI of L, right? And here you see in equation 3 rather, you are using del J del HI L. So let us go ahead, I think, with the pictorial view, then it will be more clear. So let us go ahead here. Okay, here I think. Oh, yeah. Yeah. So let us try to see. So how can we use those equations? So you see that we are first taking this third equation. So let's just go ahead with the flow and see what happens if we just employ this third equation. So for back propagation, the assumption is that you have the forward propagation done. That is this way you have done the computation. All these HJ, L-1, AIL, then HIL, etc. And if you have already computed G and also AIL, HIL, etc., that means you have also computed G prime. Just remember about or remind yourself about the sigmoid. So sigmoid is the G, and that the G prime is G into 1 minus G. So if you have G, you have G prime also, right? So very similarly, other activation functions, G prime also works in this way. So these row and this row, you have got all these things. Now, what does equation 3 says? It says del J del AIL. To get del J del AIL, you have to have del J del HIL from the previous layer. So now for the time being, assume that you have it. I think in 2 slides from here, we'll see how you get del J del HIL, which like you have computed earlier. Or basically, if I say that from here, you can get del J del HIL minus 1, that will go to the next layer, you will be convinced that, okay, I have got del J del HIL from the previous layer. And that's why it is going, it is called back propagation. You are computing it for the last layer first, then the penultimate layer, then the last to the penultimate layer, and so on, right? So let's say you have it. In 2 slides from here, you will see how we will get it for the previous layer. Here, next means previous layer. I'll just try to disambiguate here. Okay, now del J del AIL is this. This is the equation 3. And how do you get this del J del AIL? You are just multiplying this del J del HIL that you got from previous layer and the G prime HIL. So this and this gets multiplied to give you this. Now, what is equation 2 said? What did equation 2 said? That is del J del BI is your del J del AIL. So that is from equation 2. If you go back, you will find that del J del BIL is exactly this, and del J del WIL is this times some other H or something that will come. But at least you have got this, so you have got del J del BIL. This was one of our basically things that we wanted to have, that is del J del W and del J del B. So del J del B you have got. This is basically equal to the same thing. So del J del B and these are same. Now, next is naturally del J del WI. And this is the same thing, but multiplied with HJL minus 1. And you know the HJL minus 1 from the forward pass. So del J del I and del J and just HJ, if you multiply them, you get del J del W. Okay. Now the next equation, it's a little tough to basically visualize, but at least if you just kind of got the ideas from the previous 2 slides, it is easy to see. At least it's maybe, if I try to summarize the whole back propagation in 1 slide, visually it may be tough, but at least you see that, okay, you get this by multiplying G prime and del J del HIL, that is this and this. For this, it is basically equal to the same thing. For this, it is just multiplying here this and this HJL, this and this to get. Now for del J del HIL minus 1, and you see this is important because this will be used just like this for the previous layers computation of all these del J del BI and del J del WIGL. So you have to have some way to get this, and this is how you get it. This is the last equation where you just do this summation. Maybe just don't look at this. It is a little complicated, but this equation For that, you need to have del J del AML for all M and WLMI for all M. So that is like for all AM and so on. I have tried to write it. It's a little again, just take it with a bit of salt. Don't try to basically, I mean, whatever you have to remember is this set of 4 equations that you will be requiring if you want to implement backpropagation, right? So I think I have kind of sort of completed the discussion on backpropagation. If you have any questions, I know you might have many, please shoot away. I mean, you can raise your hand. Yeah, Purimal Satra, I have asked you to unmute. Yes.
So what is the use of del J del BI?
Del J del BI, you remember? So it is W and B. The parameters are, it is like WX plus B. So B also you have to write, learn. So you have to find the del J del B also, right?
Okay. That is actually del J del I, right? Del AI, sorry.
Yeah, that is actually del J del AI.
Okay.
Yeah. Because you are multiplying something which has the derivative 1. I mean, if I remember it right.
Yeah, yeah.
So this is like epsilon. It's del J. Yeah. Any other questions from anybody? Yeah, Rahul Aditya. Yeah, Rahul. Yeah.
Yes, sir, del J del HIL, sir, can be compute. Sir, if I know del J del I del HIL, then I can compute the previous layers as well, sir. But I need to know like the values for the last layer,
Yes,
so as to propagate.
That's a very good question. I will not have time for this, but if you, I will upload it in the, I mean, I thought that this will be completed last week. So I thought that this week's office hours I will discuss. But what I can do is after next week, that is next Tuesday, next Tuesday, I can also discuss, but I'll upload that document. But just to give you an idea, the last layer's H is basically that O, right? So if I can find del J del O, then we are done, right?
Yes.
You agree? So del J del O, how you can compute for a softmax function at least, I shall upload a document, right? I mean, it's, I don't remember it. It's probably, no, it's better not to take the risk. I think it is the predicted value, no, it is, I think 1, that is wherever the true class is, that will have 1 minus the predicted value, something like that. I have to see, but I can upload that. So, but remain convinced that, I mean, if you can compute this del J del O, then it is done, because the O is just HL, capital L, right? And then
yes,
from that L minus 1 and so on, you can. Yeah, that's a good question. Yeah. Any other question? Okay, if not, then yeah, I think Porimal, you have forgotten to like lower the hand. Can you please lower the hand? Yeah, okay. So let us go ahead with the next thing. I mean, this is just some illustration of employing a hidden neural network, multi-layer neural network to classify a non-linearly separable or a data which is not linearly separable training data, binary class. So what I mean by this here is you have some 2D data. So these are some x's basically, where x is just R2. Okay, red classes are positive and greens are the negatives. So you see that you cannot actually find a linear separator. You have to find probably a circular separator, sort of this. But yeah, so that's how I actually prepared the data. If you see closely, I think I have taken the radius as 7. So if the some data is beyond 7, I mean below 7, less than 7, then it belongs to the positive class. If the radius basically, or the distance from 0 to that data, and if the distance from 0 to that data is more than 7, I think I took it as 7, yeah, then that is negative class. So how can you basically learn a or can we learn a boundary which is not linear, using say single hidden layer neural network, a 2 hidden layer neural network, and so on. So we have seen it that using a perceptron algorithm, we could not do it, right? So I have given one illustration probably 2 classes back. Okay, so this is the training data. So this much data you have as training, and let's see. So this is the learned decision boundary with single hidden layer. So if I just use the single hidden layer, that is input layer, a single hidden layer, then the output. And I have used, if I remember it right, just the ReLU activation functions in between. And how do you interpret this? That I have taken the same area, that is plot between -10 to 10, or even I think -11 to 11, whatever. But it includes that 0 to 7 and 0 to 10, etc. So I have just densely, I mean, I have trained with this data. I have trained with this data, whatever this data is. And then when I tested, I took very dense, basically, points from here to here. Lots of samples, and in this direction and in this direction, and I passed it through the trained network and saw what is the predicted class of that, and then I just plotted them. So if the predicted class is red, then I predicted class is positive, then I colored them as red, and if the predicted class is negative, I colored them as green. So is there any question on to interpret the color of this? And these 8 variations are again with just single hidden layer, but with different amount or number of hidden neurons. So single hidden layer with 2 hidden neurons, you see it does not do a good job. So it does not have the requisite number of complexity. You can think that this is probably a underfitting. But for that, again, you need to see the test data, train error, plot, and so on. But I mean, you can guess that only 2 neurons in the hidden layer may not be enough to learn a very, it's not a complicated, but at least nonlinear decision boundary. Even I increase it to 4, it is trying to learn a nonlinear classification boundary, but it's very much not true, right? I mean, very small certainty is given. Then hidden neurons, if you increase it to 8, it does a better job. Probably with 16, it does a little more better job. So though the actual boundary was at 7, it is giving it as at least 5, right? Now for hidden neurons is 32, this happens 64. You have to play with it, right? So you have to see and so on. There is not a set rule that this will work good or that will work good, because there are lots of hypotheses. Even in one single hidden layer, you can take, I mean, I have taken 2 and 4. Why not 3? Why not 5, 6, 7? So these questions can come, but there is not much a way of basically knowing that in advance. If you know it, then ML problem is solved. And there are ways to basically decide, not ways, I mean, questions about deciding about the activation functions, which activation functions to take, how many layers, and so on. So this is again the same data. I mean, again, the trained 2 hidden layer neural network. If the number of neurons in each hidden layer is 2, that is 2 and 2, then 4 and 4, then 8 and 8. This sort of way. I tried to just give you a flavor of it. Nothing else. I think I'm done with this lecture. I still have like 10-12 minutes. I will go ahead with the next topic. At least it will get started. But before that, I see one raised hand. So Rishabh, I have asked you to unmute.
Hello, sir. Am I audible?
Yeah.
Sir, actually, while discussing the backpropagation, we were using the ReLU function. So, sir, means ReLU.
No, while using backpropagation, I did not.
Means sorry, while using sorry means I meant to say you are using ReLU. So, sir, the point is
here. I mean, yes. in this, yeah.
No, in general, sir. In general, when we are using ReLU.
No, so, in general, you can use anything. I mean, whatever I discussed with backpropagation or this, you can do with any activation function. Yes.
So, sir, the point is ReLU, sir. In ReLU, before x less than 0, the gradient is 0, sir.
Right.
So, sir, means we are saying that when value is 0, we don't want to make system learn. So, sir, we don't want to backpropagate.
No, it is not that. It is not learning for that particular neuron, but it can be non-zero value for some neurons in its previous layer, some neurons in its next layer. So only for that neuron, it may not learn. But again, if you change the weights of some of the previous layers in the next iteration, I am saying, when you have done one gradient step, so you are doing it for all the neurons in previous layer, in next layer, and so on, right? It concerns more with the previous layer. So if the previous layer's weights are changed in a way that this neuron's activation value now is more than 1, that can happen, right? You have changed all the weights in the previous layer. So then it will start again learning, right?
Okay, but sir, this is like very confusing because we are saying that we won't.
What is the confusion? There is no confusion.
Because in tan or sine, we are saying that.
Sorry.
Sir, in sinusoidal, we are saying that we will learn whatever the case is, like x is 0 or x is greater than.
No, here also you will learn. But suppose you have learned what all you had to learn. Why will you learn again? Suppose you are doing that. Okay, I will do a MTech. That's what, and whenever, and you, after you got the MTech degree, why will you learn? I mean, just I'm giving a funny example, but it might be that it has learned its job. It can correctly classify everything. Say, then why will you learn? So you don't have to learn for learning's sake, right? So that is one, again, higher level philosophical answer. Another thing is that you can also have, I mean, people have thought about it. You can also have something called p-ReLU. It's called leaky ReLU. So here it is not like this, but it has small gradient for the negative ones. There are, I think, called g-ReLU also, where you have some Gaussian function here and so on. So all those details I don't remember from the top of my mind, but there are variations of ReLU also. Okay. So both way you can try to convince yourself. Okay. Okay. Any other questions on this topic? Gautam Sagar. Yeah, I have asked you to unmute. Yeah.
So we are using, we will use back propagation with only the gradient based optimization method, right?
I did not get the first part of your question. I mean, some noise is coming.
So I'm saying that we can only use this back propagation learning algorithm with some gradient based optimization.
Yes.
So, sir, what if we want to use some other optimization algorithm which
about it? I mean, I think the optimization class. Do you remember that evolutionary algorithm I just touched? I just touched it. I did not. So gradient or evolutionary, I mentioned about it. But yeah, I mean, this is the most popular way. People can use those.
So if you want to use genetic algorithms or some other algorithms, optimization algorithms, then how we can incorporate those optimization algorithms with the
that is a topic
learning
that is covered in genetic algorithms. Okay, you have taken it, it is fine. Otherwise, there are many online courses that you can take. This is not beyond the scope of this lecture. Okay, I think I see one more question. I'll take this as the last question for this topic. So, Anupam. Yeah, I have asked you to unmute.
Sir, my question was, we are computing a lot of delta J, delta W, delta J, delta I, and then we're multiplying by step functions, sir. So by the time we reach the first neuron or the input layer, the weights for that, don't they get like very little perturbation because like we're multiplying so many things?
They can get. There are ways to fix it. We will take, I mean, if it is very deep, then they can get. But generally, if you have lots of data, that is sort of one hypothesis that people give, that you reach a minima which is flat, so you don't generally fall from that minima. But yeah, that's again very high level explanation. But yeah, that can happen. That is called gradient vanishing problem. We will see how we can deal with it when we basically discuss the recurrent architectures. There the problem is more.
Sir, so when the number of hidden layers is larger, we will face this problem, right? Not when the number of
Yeah,
neurons.
I mean, you can get, but the chance is more when you have very deep neural networks. Okay.
Okay, sir. Thank you, sir.
Okay, let us go ahead with the next part, for which I need to actually switch to. Is it? I need to switch to my laptop. 1 second. Yeah, I will share. Yeah, Anupam, can you lower your hand? Yeah, I shall share my screen. Just I'll start this. Yeah, here it is. Okay, hopefully you can see my screen, and yeah, just give me 1 second. Yeah, just give me a second. Share my screen. Oh, I'm screen sharing already. Okay, sorry. Close it. Yeah, then. Yeah, so let us try to just briefly start what we will basically continue next day. So we will actually start this thing, that is our goal is to cover the sort of basics of convolutional neural network. So we have done using what is called the deep, I mean the artificial neural network, but there is a little different thing called the convolutional neural network, and which is a main driver behind the popularity of deep learning deep learning literature. And we will also go through transformer, but not now. I mean, I think we plan to basically do this in March, and then there you will see we will come back to this artificial neural network again. So, but let us try to sort of cover the basics of convolutional neural networks, building on the ideas of the ANN, artificial neural networks, that we discussed just now. Okay, so here. Okay, now before going there, this is a very fun slide, the importance of MNIST. So as you see, if you want to have deep learning on your resume, then probably just you can jump all these things, linear algebra, calculus, probability, machine learning, and just try to use a tool called Keras and try to say do MNIST classification. So this is again a fun slide, but yeah, I mean, what you actually need to do if you want to learn deep learning good, then of course you have to have some knowledge of linear algebra, calculus, probability, machine learning, etc. So we are actually doing this. We are taking this slow and steady path and going, I mean, not just jumping steps, right, and going there. So again, this is the fun slide, but the important part is this MNIST dataset. So let us go to this, because we will need this to discuss how convolution comes into being. So MNIST is a dataset which is a database of handwritten digits. So it has 10 classes. That is 0, 1, 2, 3 to 9. So 10 digits from 0 to 9. And it has images of these handwritten digits. So it has 60,000 images in the training set, and test set has 10,000 images. I think it is equally divided. That is, each digit has 6,000 training images and each digit has 1,000 of test images. Generally, it is divided in this way, that 5,000 images for each digit is taken as training and 1,000 as validation. That makes this 6,000 images and 1,000 for test. Now, these are all grayscale images. So let me just try to have the pointer. Where is your spotlight? So just 1 second. here, spotlight. Yeah. So this, so these are grayscale images of size 28 cross 28. So what this means is that this size is 28 pixels by 28 pixels, all these images, and these are grayscale. That is, it has only one channel. Color images has 3 channels, you know. RGB generally is the way to basically represent them. But here you have only one channel, that is one matrix, 2D matrix of 2D, 28 by 28. Each of these 28 times 28, that is 784 values, will have some intensity values. So of course, the intensity values are high for these white pixels and low for these black. So completely black means 0, and completely white means 255 sometimes, or 1 sometimes, because it depends on just the scale. Unless we need the value 1, we will just assume that it is 255, 8-bit image. Now, often treated, so this data set is often treated as the hello world for any MLDL practitioner. So basically, you, if you can do a classification on this, and this is like the hello world that you have done for MLDL. Now let us go ahead. So this is one example from MNIST. So you have seen some data from MNIST just in the first, the previous slide, this one. Now this is one of them, just 7 out of those 6,000 or 7,000 sevens that you have in MNIST. And these are the intensity values. This is just 28 columns and 28 rows. The 784 intensity values. So this is the first one. The 008 value is 0, that is, it's completely black. The next one is 0, that is completely black. This one, and so on. Now here you see that you start to have some values, 21, 61. Maybe these are the values, 21, 61, and so on. Now, if you try to see, this is the image and this is the intensity values that I have just given it as the values in a 2D array. Now, can you discover a pattern in this intensity values, the way it is arranged? So, so that you can answer, I can just try to unmute you. 1 second. Where is it? Yeah, I'm just giving you permission to unmute yourselves. So, can you see a pattern if you just try to focus on the intensity values? Say, the non-zero values, right? Can you see a pattern here? If you look closely, focus on this area.
7.
Yes, sir. 7.
Yes. So if you just closely look on this area, you are finding a 7. So if I now take it back, you see it, right? So all these non-zero values are arranged in pattern of 7. So I'll just go into this slide, and then probably we will stop. So this motivates us to use actually some sort of a weird window. So a window which looks like a 7. So we are trying to say find a 7 in an image. So if I go back in this, we are trying to see, we don't know, say, that what digit it is, no level is given. We means here the model, the machine learning model. So you basically try to find a 7. So can we have a window? The way it is, you can think that you have a window that is all black, but only the part which looks like 7 is white or transparent from where lights can come, and you just are you are wearing it in terms of some sort of like a blinkers or blinders that you generally see on horses in a horse cart. So these horses are given these blinkers so that it cannot see anything else other than what is in front. So some sort of a blinkers, you can think of this as this window, and you can only see what is directly beneath those transparent glass or transparent part of the window. So just to tell about this, so this is the transparent part, the white part, and it's again a weird window. So you can only see what is directly beneath this, not here. So I have made this window using the pattern here. So whatever is non-zero, I have just told that these are my transparent signals. So this is the transparent pixel, this is the transparent pixel, this and this and so on. I have just put 1 there and everything else is 0. So let us see how we can use this window to classify a 7. So what we will do, this is called a filtering operation or convolution operation. That is where the name convolution comes from. But what it is, let me just tell, and then we will conclude. it is like 59, but yeah, like 1 or 2 more minutes. So this is the window, the red bordered one, and this is suppose 1 digit of 7, which we don't know whether it is 7 or 5 or 0, but we would try to see if there is a 7 through this window. What we will do, you just take this and try to put it on this image. So it is not putting directly on it, but say with some overlap. For simplicity, what I have thought is that, okay, this filter, I mean, this window is also called a filter also. So these are interchangeably used. So this window, you can say just overlap this last pixel, last column of pixels with the first column of it. Then you slide 1 more pixel. So you slide so that the last 2 columns of it and the first 2 columns of it are overlapped. Now, if you think that if just the last 2 columns are overlapping here, that is last 2 column of this and first 2 column of it, you will not be able to see anything through this window. There is nothing here of 7. So you just go ahead and slide. Now, the amount of pixels that you want to or you get to see, you can have a measure of it by just trying to sum what are the pixels that you can see behind this window. So if you can see a pixel, just 1 pixel through it, whose intensity is say 5, the sum is 5. So you can measure that, okay, the amount I can see is 5. Maybe there are 2 pixels that you can see, one is 5, another is 8. So the sum is 5 plus 8, 13. So that way you can just give a number. So if you do this for say this much of overlap, the sum is 0 because you can't see any pixel here. Now, if you go ahead and you slide more, you see this part because this is the overlapping part. Okay, so I mean, you are just overlapping this red on the blue, and only some of this part through it, you will see some, say some of this part only. That is only the overlapping parts. Okay, so if you sum those intensity values, that is in here, basically the sum somewhere here, it might be that value, this 1410. Similarly, you go ahead, you slide it more, you are getting more and more intensity values to see 4098, 18604 when there is a fully overlap, and you just go ahead there and it decreases. So you see that you can actually get a high overlap value if there is a 7 there. So how can you use it? You take windows or filters or prototypes for different such classes. Say for the class 7, it is basically this window. For class 5, it is this window, and these are the test images. That is, you don't know which digit it contains. So what will you do? You take this filter, you slide it through it. What is the value, maximum value of the sum that you get? You take this window, you slide over this image. What is the maximum value for this operation? That is sliding 5 over 7, 5 window, or sliding the window for 5 over this test image. You get that maximum value. You slide this 8 over this, you get the maximum value. You get you slide 9, the window for 9 over this, you get a maximum value. So you get 4 values for this test image. Now, whatever is the maximum value, or which window is giving you the maximum value, that window's class will be this class. So that is the basically very naive way of classification. It is called classification by matching filters. So you are trying to match this window to whatever is there in this pattern. Similarly, you can do 7 over 5, the window for 7 over 5, the window for 5 over 5. And hopefully this, when you slide this 5 over 5, it will give you the highest value. So that is a particular way of classification by matching the filters. But I will leave with this, that what if the test image is a little rotated or skewed or zoomed out? These are some of the general, I mean, natural variations, right? The images can be a little, I mean, not all 7s look like this. Maybe not all 7 looks like this window. Maybe not all 5 looks like this 5. It may be a little rotated. It may be skewed, stretched. It may be zoomed out. So what will happen then? Will we get this? So I'll leave this with this question. If there is any other questions from anybody, you can raise your hand and basically I can try to answer, and tomorrow we will meet again. Yeah. If there is any question. We will talk about the presentation logistics tomorrow after the class. Okay. if you have any questions. I have answered a few during the office hours yesterday and at the beginning of the class also.